Good day, students. In this clip, we're going to be going over an example on how to use implicit differentiation to describe the tangent lines at different points on the curve of a rotated conic section. So let's go ahead and take a look at the problem. It says for the curve with the equation x squared plus y squared plus xy minus 18 equals 0, part A, we have to find the slope dy dx at any point xy on the curve of the equation. B, determine if the tangent lines to the curve at the x-intercepts of the curve are parallel. And then last part C, find the points where the curve has vertical and horizontal tangent lines, okay? All right, so just a point to note is that an equation of this form represents an ellipse that has been rotated, okay? So it's a rotated ellipse. This one is rotated about the origin. Okay, so let's start with the A part. Part A, we have, let's write this down. Part A, we want to find dy dx. Okay, we want to find dy dx at any point xy on the curve that this equation represents. Okay, so this is an implicitly defined function, so we're going to have to use implicit differentiation to find dy dx. All right, so the original function is x squared plus y squared plus xy minus 18 equals 0. Okay, so what I'm going to do is differentiate both sides of this equation with respect to x. Okay, so we're going to take d dx of x squared plus y squared plus xy minus 18. Differentiate the left side with respect to x, and then you also differentiate the right side, d dx of 0 with respect to x, okay? All right, so just remember the whole idea of implicit differentiation. Differentiate each term, and then if the term doesn't match the denominator they're differentiating with respect to, you have to append d of that variable dx after differentiating. It's just like the chain rule, okay? So let's go ahead and differentiate this term by term. If I differentiate x squared, I'm going to have 2x. The variable matches with that, so I'll have dx, which cancels out to 1, so there's no need to add anything here. Plus, now y squared, I'll differentiate y squared, the derivative of y squared is in the power rule, is 2y. Now, these variables differ, so I'm going to have to add dy dx, okay? Now here, xy, we're going to have to use the product rule because we have a product of two functions, x and y. So this can be viewed as my u, and this is my v. And you know what the product rule is, right? So uv prime can be written as vu prime plus uv prime. Or you can also say uv prime plus vu prime. You know, addition commutes, so it doesn't matter. I like to use this formulation. So let's just use this one, okay? So we're going to have plus v is y, u prime is the derivative of x, which is just 1. I don't need to add dy dx because it's going to be dx here, which is just 1, all right? Plus, we're now going to do uv prime. So u is x, the derivative of y is 1, but since we're differentiating with respect to a different variable, we have to add d of that variable y, d, the variable we're differentiating with respect to, which is x, okay? All right, and then if you differentiate the constant 18, is just 0, okay? And then the derivative of 0 is just 0. Okay, let's go ahead and simplify this a little bit. So we're going to have 2x plus 2y dy dx plus y plus x dy dx equals 0. Okay, so to get dy dx isolated, what we're going to do is collect all the terms with dy dx, put them on one side, and all the other terms, move them to the other side, all right? So if you notice, 2x and y do not have dy dx attached to them, so we're going to move them to the other side. And on the left side, we'll have 2y dy dx plus x dy dx equals negative 2x minus y. Okay, if you subtract 2x and y from both sides. Now on the left side, I'm going to factor out dy dx because it's common, so factor that out. Dy dx times 2y plus x is equal to negative 2x minus y. And then finally, to get dy dx isolated, I'll divide both sides by 2y plus x, so 2y plus x, and divide the other side by 2y plus x. All right, so your final answer, dy dx, is equal to negative 2x minus y over 2y plus x. So this equation helps you calculate the derivative at any point xy on the curve of the rotated ellipse. Okay? All right, let's shift our attention to part B. In part B, we were asked to find, let's go back up, determine if the tangent lines to the curve at the x-intercepts of the curve are parallel. All right, so let's label it. So for the B part B, we're going to find tangent, slope of tangents at the intercepts. Okay, so let's title it slope of tangents at x-intercepts. Okay, we know what the slope of the tangent is, right? That's basically what the derivative basically is the slope of the tangent line. So we're basically examining the derivatives at the x-intercepts and seeing if they're the same, which implies that the lines are parallel, and then if they're different, then the two tangent lines at the intercepts are not parallel. Okay. All right. So how do we figure out the points where we have the intercepts? If you have your x-intercept, that implies that y has assumed a value of 0. Okay, when y is 0, that's where the curve intersects the x-axis. Okay, so what we're going to do is plug in 0 into your original function. Plug in 0 for y. So let's recall our original function, x squared plus y squared plus xy minus 18 equals 0. So I'm going to plug in 0 for y, solve the resulting equation for x. That will yield the x coordinates of my the x coordinates of the x-intercepts, and then I'm going to just pair them up with the 0 that I have for y. That will give me my x-intercepts. All right, so let's go ahead and make the substitution. First, we're going to have x squared plus 0 squared plus x times 0 minus 18 equals 0. All right, so let's simplify this. We're going to have x squared minus 18 equals 0. If you subtract 18 from both sides, add 18 to both sides, you have x squared equals 18. And then if you root both sides, you have x equals plus or minus 3 root 2. Okay, when you take the square root of 18, you can break it down. It comes out to 3 root 2. Okay, so your x-intercepts are negative 3 root 2. What is the y coordinate? Is always 0, right, at the x-intercept. And 3 root 2, comma 0. All right, so there goes your x-intercept. So the question is, is the slope of the tangent line at these 2 points the same, or are they different? Okay, so let's go ahead and evaluate it. So we want to determine what dy dx is at two fixed points. So let's evaluate dy dx at the first point, negative 3 root 2, comma 0. Remember this, the other solution we got tells you dy dx at any arbitrary xy point. Okay, so now we're making use of it to find the slope at a fixed point. So this simply means we plug in x and y into this equation. Okay, so we're going to have negative 2 times negative 3 root 2 for the x minus y is 0 over 2 times y, which is 0, plus x, which is negative 3 root 2. Okay, if we work this out, we're going to have 6 root 2 over negative 3 root 2 And then when you divide this out, you get -2. Now, what does this answer mean? This answer means that at this intercept, the slope of the tangent line is -2. So the question is, what is the slope at the other intercept? Are we going to get the same thing? If we do, then that means that the tangent lines are parallel at the x-intercepts. If not, then they are not parallel. Okay? All right, so let's go ahead and find it out. At, say, at 3 root 2 for x and 0 for y. All right, so what we're going to do is plug in these values that we're evaluating the slope of the derivative at into the equation of the derivative that we got earlier in part A. Okay, so we're going to have -2 times 3 root 2 minus 0 divided by 2 times 0 plus 3 root 2. Okay, we'll multiply across, simplify the numerator. We're going to have -6 root 2 over the denominator 3 root 2. The root 2's cancel out. 3 goes into -6. -2 times, so your final answer is -2. Okay, so the two slopes are the same. So what does that tell us? Let's go ahead and write a conclusion. So since both slopes are the same, since both slopes are the same, the tangent lines are parallel at both points. Which are, what are they? They are the x-intercepts, right? Which are the x-intercepts. All right, so there you have it. All right, let's shift attention to part C. In that part, we're asked to find the points where we have vertical and horizontal tangent lines. Let's start off by finding out the points where we have vertical tangent lines. Okay, so let's write down the title, vertical tangent lines. So you know what a vertical line looks like, right? It goes up and down. What is the slope of a vertical line? It's undefined because you have 0 run, okay? So how do we find the points where we have vertical tangent lines? Or what's the situation with the slope when you have vertical tangent lines? When you have vertical tangent lines, those are the points where the derivative is undefined because you have undefined slope. The derivative is undefined, or the denominator of your derivative is equal to 0. Okay, so any value that makes the denominator of your derivative expression to equal 0, that value will result in a point of vertical tangent. So this idea is basically going to guide our problem solving process, all right? So we see that we have a derivative expression. So what we're going to do is we're going to extract the denominator and set it equal to 0 because that's what will make the derivative expression to be undefined. So the denominator is 2y plus x. We set it to equal to 0. Okay? So let's solve this for x. If I solve this for x, subtract 2y from both sides, you have x equals -2y. All right, so that goes the relationship of the point where you have vertical tangent lines. Okay, so let's use this to find the points. Okay, so how do we do that? In order to accomplish this, what we're going to do is we're going to take full advantage of this equation. First use of this equation is in generating a solvable equation where we can find the values, the numerical values where one of the variables is on a point where you have a vertical tangent line. So to do that, we're going to, since we have x explicitly solved for, let's recollect what the original equation is. So the original equation is x squared plus y squared plus xy minus 18 equals 0. Okay, this is the original equation. I'm going to substitute negative 2y for x, which will give me a solvable quadratic equation. All right, so let's make the substitution. We're going to have negative 2y squared plus y squared plus negative 2y times y minus 18 equals 0. Okay, this will enable me to find the y-coordinates of the points where we have vertical tangent lines. All right, so let's solve this, simplify this. We have 4y squared plus y squared plus, I'm sorry, minus, because minus times plus is minus, minus 2y squared minus 18 equals 0. All right, let's see. So we have 4 plus 1 is 5, minus 2 is 3. We have 3y squared. Add 18 to both sides equals 18. Divide both sides by 3. We have y squared equals 6. Let me show you all the steps. So you take the square root of both sides. And then you're going to have y is equal to plus or minus root 6. Okay? All right, now we're going to find, these are the two y values where you have vertical tangent lines. So now we need to generate the x values where we have vertical tangent lines. Okay, so when y is equal to negative root 6, what is x? We can just use this equation again. So that's going to imply that x is going to be negative 2 times negative root 6. Okay, that's what this relation tells us, that at the points where we have vertical tangency, x is the negative double of y. Okay, so that's what I'm doing here. So if we work that out, we're going to get, this is going to be equal to positive 2 root 6. So that yields 1 point. And also, let's split this down the center. When y is the other value, root 6, what is x? Use the same equation. X is going to be, well, that implies that x is going to be negative 2 times root 6. Okay? X is going to be negative 2 root 6. So the points where you have vertical tangency, so let's write that down, points of vertical tangency. Remember, these are the points where this derivative is undefined. Vertical tangency are, let's use the first pair. This is the x coordinates, 2 root 6 comma negative root 6, and the other one, negative 2 root 6 and root 6. Okay, in the next installment of this series on implicit differentiation, I'm going to show you the graph of this rotated ellipse, and I'm going to show you why all these answers make sense. Okay, all right, so let's shift attention to the point of horizontal tangency. Okay, shift our attention there. All right, so let's go ahead and find the points where we have horizontal tangent lines. Okay, let's title it. This is still part C. Horizontal tangent lines. Horizontal tangent lines. All right, so the question is, what does a tangent line, what does a horizontal line look like? Horizontal line looks just like this. What I just proved is a horizontal line goes side to side, right? And we know the slope is 0 because you have 0 rise, right? But you have run, you have 0 rise. So the slope is 0. So what does that tell us about dy dx? Since the slope is 0, you have a horizontal tangent line where dy dx is equal to 0. So all you simply do is we're going to set that derivative equation we came up with earlier to 0 in part A and solve. And then it shows relationship between x and y at any point where we have horizontal tangent lines, all right? So let's set dy dx to 0. So we're going to have negative 2x minus y over 2y plus x equals 0. Okay? So what we'll do next, we'll just cross multiply. With cross multiply, that's going to yield negative 2x minus y equals 0. if you let's see, I want to get y by itself. If I add y to both sides, I'll end up with y equals negative 2x. Okay, so this is the relationship that shows the relationship between, it's the equation that shows the relationship between x and y at every point will have horizontal tangent lines. Okay, but we're looking for points. So how do we find the points? Well, I need to find some numerical values. So what we're going to do is exactly what we did when we're looking for the vertical tangent lines, right? We're going to plug in negative 2x for y in the original equation and then solve the resulting quadratic equation for x, okay? So let's recall what the original equation of the rotated ellipse is x squared plus y squared plus xy minus 18 equals 0. So we're going to plug in negative 2x for all the y's, okay? So we're going to have x squared plus negative 2x squared plus x times negative 2x minus 18 equals 0. All right? Okay, so let's see. Let's simplify this. We're going to have x squared plus 4x squared minus 2x squared minus 18 equals 0. It's exactly the same as this one. The only difference is the x's are y's, you know. Okay, so let's simplify this. 5 minus 3 is 5 minus 2 is 3, so we have 3x squared. Add 18 to both sides equals 18. If we divide by 3, we have x squared equals 18. And then if we solve for x, we have x equals, I'm sorry, I messed up. If we divide both sides by 3, you have 6. So 6, and if you root it, you have plus or minus the square root of 6. Okay, so let's find the points. We have the x values. Now to find the y values, all we're going to do is input our two x values into this equation right here to determine the y coordinates of the points where we have horizontal tangency. Okay, so let's do it. So when x is a negative value, negative root 6, y is going to be negative 2 times negative root 6, which is equal to positive 2 root 6. Okay, and then when x is the positive value, root 6, then that implies that y is equal to negative 2 times negative 2 times root 6, negative 2 times root 6, which is equal to negative 2 root 6. Okay, so there you have it. So now our points of horizontal tangency are they are negative root 6 comma 2 root 6 and root 6 comma negative 2 root 6. Okay, it's basically the inverse of this point. If you switch these two, you get this, and if you switch these two, you get that. Anyway, so there you have it. So on the next installment to this, I'll be showing you the graph of this rotated ellipse, and I'll show you a graphical representation of the vertical horizontal tangencies and the slopes on the x-intercept, illustrating the fact that they are both parallel. All right, so there you have it. So thanks so much for taking the time to watch this tutorial. Feel free to subscribe to my channel so you can get updates to the next part of this installment and other cool calculus clips such as this. And also post a comment to let me know what you think about this presentation, and click like if you liked it. Feel free to share it with your friends on your social networking program. More clips can be found on matgosub.com/calculus. Thanks again for watching and have a wonderful day.